So we need to know about how this lipid bilayer is really. Now, it's not just the phospholipids that are in a line, because if it was just the phospholipids, we wouldn't be able to achieve the functions that the membrane needs to achieve. And so one of the things that scientists came up with was an explanation that we have the lipid bilayer, and there you can see it, and it's less diagrammatic here. You can see that the tails are a little less organised as opposed to two straight lines. And punctuating, which means every so often sticking through this lipid bilayer, are proteins. And proteins will have different functions, and they will have different levels of passing through the plasma membrane. So, for example, this one passes all the way through in the middle, but this red one is just an intracellular on the intracellular side. This one here is simply on the extracellular side, and this one passes all the way through. So the proteins are sitting in the plasma membrane, and they are going to be important for both the structural integrity of the plasma membrane, for recognition of the cell. For example, this one here could be a receptor, and so imagine if it was a hormone receptor and insulin was coming along the bloodstream, and it had a bit like an enzyme's active site, a certain receptor shape that fitted an insulin molecule, then the insulin could come and bind, and that would affect the inside workings of the cell because of this receptor on the outside. The proteins that traverse all the way through a lipid bilayer might be involved in transport, getting through the lipid bilayer, which otherwise wouldn't get through without help. And we're going to learn about what those are shortly. So, they also add rigidity, which is also assisted by cholesterol being in the plasma membrane as well. And the amount of cholesterol will affect how stable and how fluid the membrane is. And that is why cholesterol is a very important part of your diet. You've got 100 trillion cells, they've all got plasma membranes, and they're all going to need cholesterol in there. And so fats and cholesterol are a very important part of every cell. Obviously, you just don't want to have too much cholesterol. So this is the fluid mosaic model, which talked about the proteins moving around. And imagine that olive oil analogy I talked about, where it's a very fluid type of arrangement. Okay. And this came to be accepted as the recognised way that the membrane looked. Okay. So here we can see the proteins moving around in a fluid way. So how does that look in a diagrammatic sense? Now, in a diagrammatic sense, we've got the phospholipid bilayer here, which is, as we saw before, phosphate heads, lipid tails, phosphate heads. And here we can see a more diagrammatic way of what we've just seen in 2 dimensions. We have a protein that traverses the membrane, and this offers, and this is an important term, a channel for substances which might be able to come through the membrane. Okay. This glycoprotein here is, on this side, is used for recognition, and glyco is sugar, protein, and so it's a protein with a carbohydrate chain attached, and this can be used for recognition and cellular-to-cellular contact. So imagine 2 cells coming together, they would be able to, if there's a conformational fit, which means shape fit, once again, a bit like active sites and enzymes, they'd be able to interact because they have got a complementary shape due to the glycoproteins here. We've got enzymes, which are proteins, of course, on the intracellular side here, and as I was talking about earlier, a receptor here, which might have a conformational fit to a hormone. So there is the diagrammatic sense of the proteins that, as I would say, punctuate, which means are inserted into the plasma membrane with the phospholipid bilayer. Okay. Remember, this is the inside of the cell, so this is aqueous, and this is the extracellular outside of the cell, which is also aqueous, and that's why the phosphate heads are aligned that way. This would be a really oily film in between them. Okay. Now, do you think you could label those in terms of the glycoprotein and what's it for, the channel protein, the receptor, or there was an integral protein, which is just a protein that adds structure? Could you label those? Or if you want to press pause now and label them, just to double check you can, we can move on and you will have a good basis for the knowledge of the membrane. And if you pause it then, can you name them all? And then I'm going to reveal them shortly. Okay, so there they are. So, we now can come to what can pass through the membrane and what can't. Okay, and we've learned at GCSE that the plasma membrane is a controller of what goes in and out of the cell. And now we need to go into more detail, because the structure of the lipid bilayer, and I mentioned this earlier, means that if something can dissolve in oils, and that means it's non-polar, it doesn't have a charge, then it can interact with this lipid, the oily section of the membrane. And therefore, fat-soluble molecules, or non-polar molecules as we call them, can pass straight through the plasma membrane. This is really important. So if there was a hormone, for example, that was a steroid hormone, and therefore was soluble in the lipid bilayer, it can actually go straight into the cell and affect gene expression, or the metabolism of the cell, without having to interact with any of the proteins. The other thing that can go through the membrane, which is not actually here, are very small non-polar molecules, like oxygen gas or carbon dioxide. And they are able to diffuse through simple diffusion through the lipid bilayer. We kind of think water can as well, although water is polar and so should not be able to go through the lipid bilayer. Water undoubtedly does go into the cell, as you might expect, and out of the cell. And we think this might be some specific channels called aquaporins, a bit like this protein channel here, but for water. Although the jury is still out on that. But it is weird that water can go through, and yet water could not interact with that lipid bilayer. As you know, water and oil don't mix. The next one, though, so we've got fat-soluble molecules, and we've got very small non-polar molecules like oxygen, which is a crucial one. Then we've got polar molecules. Now, when I say polar molecules, I'm talking about things like ions. Imagine sodium ion, Na+. Now, Na+ will interact with water, and it will form actually quite a clunky hydrated ion. And anything charged will not be able to interact with the lipid part of the bilayer. And so we need to have a channel protein. And so polar molecules will not go through the lipid bilayer by themselves, but they need what's called a channel protein to get through. And this is a huge function of the proteins in a lipid bilayer, in a plasma membrane, because they allow molecules which are polar or very large, which otherwise wouldn't have been able to go through the lipid bilayer, to get through.